Hello friends, today we will continue with studies on eccentric connections. Eccentric welded connection, moment at right angles to the plane of weld. Today we will start with design problems. Let us consider an eccentric connection. Let this be in column. For this column we are going to connect a bracket. Let this be load P. Eccentricity distance is E. This bracket is connected to the flange of the column by weld. Let this be the welded portion. Now let me draw another view in this direction. Let this be the bracket. For this bracket, this is the weld which I am going to provide on both these sides. Let this height be h, height h of the weld. This be the throat thickness T. Similarly, h I can show it here. So consider load P at eccentricity E. Moment M is equal to P into E. We have some standard equations. Depth of weld required h dash is equal to under root 6m by 2 into T into FWD, where 2 indicates 2 line of welds, T is throat thickness of weld, FWD is characteristic strength of weld, and that is given by Fu by root 3 gamma mw, where gamma Fu is 410 newtons per mm square, root 3 gamma mw is partial safety factor. Now you round off the height of the weld required. H is approximated to 1.1 times H dash. Now go for the check for stresses. Once you finalize the throat thickness and find out H, you need to check whether stress in the extreme weld is less than characteristic strength, that is Fu by root 3 gamma mw. So check for the stress is given by the equation under root 3 F1 square plus F2 square. This should be less than characteristic strength, that is Fu by root 3 gamma mw, where F1 is direct stress, and that is given by P divided by A, where P is load, A is area of weld, and again area of weld is given by throat thickness into total length L. F2 is stress due to bending moment, and F2 is given by the equation 6m by 2t into h square, where 2 indicates 2 line of welds, t is throat thickness, h is total height of weld, m is bending moment. Let us take one design example and try to solve using these equations. Design A. Suitable fillet weld for the bracket shown if load is 100 kilonewtons and eccentricity is 150 mm. Thickness of bracket plate is 12 mm and column used is ISHB 300 at 618 newtons per meter. Now let us draw a diagram. For this we are going to connect a bracket. This bracket is subjected to load P is load P. Eccentricity is 150 mm. For this we are going to provide welding all along the bracket on both these sides, two sides. Let me draw another view. So this is the view of the flange of the I section, ISMB 300. This be the bracket. For this bracket we are going to provide weld of thickness T on both these sides. Thickness T. Let P is equal to 100 kilonewtons. Working load or ultimate load for design consideration is 100 into 1.5, that is 150 kilonewtons. Eccentricity E is 150 mm. Moment M is equal to P into E. 150 into 10 raised to 3 into 150 Newton EMS. Now let me find out the thickness of the weld required. This column is given as ISHB 300 at 618 newtons per mm. This is connected to a bracket which is 12 mm. Now first I have to determine where to finalize the minimum thickness of plate. This flange interacts with this bracket. So I need to find out what is the thickness of this. Flange thickness of ISHB 300 is 10.6 mm from steel tables. I get this value from steel tables. Next, minimum size of weld. Three mm. maximum weld size is equal to thickness of thinnest plate. So I am going to compare 10.6 with 12. So thickness of thinnest plate is 10.6 minus 1.5. So I get 9.1, say 9 mm. So size S is equal to 9 mm. Throat thickness T is equal to 0.7 into S, 0.7 into 9, that is 6.3 mm. Next, characteristic strength of weld. Characteristic weld strength FWD is equal to FU by root 3 gamma MW. So FU is 410 root 3 into, let us consider shop welding, so 1.25 factor of safety, partial safety factor 189.3 newtons per mm square. Depth of weld required. Depth means this height. First I am going to calculate H dash. From H dash I am going to calculate H. Depth of weld is equal to H dash is equal to 6 m by 2t into FWD. So that I am going to calculate 6 into m, moment m, 150 into 10 raised to 3 into 10 raised to 3 divided by 2 into throat thickness, that is 6.3 into FWD, that is 189.33. So H dash I get it as 237.86 mm. H is equal to 1.1 into H dash, so that I get it as 261.64. say I am going to round it off to next round figure. Say H is equal to 270 mm. Actually design problem completes here. I know the thickness of the weld required, and I know height of the weld required, but I have to ensure that stress in the farthest point, critical point of the weld, it should be less than characteristic strength. So for that we are going to do check for stress. Direct stress is equal to F1 is equal to P divided by A. So load P is 150 into 10 raised to 3. A is cross sectional area. Throat thickness T into height H 2 times. So that I am going to get 2 into T into H. So I get 150 into 10 raised to 3 divided by 2 into 6.3 into 270. So I get 44.09 newtons per mm square. Next, stress due to bending. Is equal to F2, that is given by 6 m by 2t into h square. So 6 into moment m, 150 into 10 raised to 3 into 10 raised to 3 divided by 2 into 6.3 into 270 square. So F2 we get it as, out working out, 146.97 newtons per mm square. Now check is under root 3 F1 square plus F2 square. This should be less than characteristic strength. Under root 3 into 44.09 square plus 146.97 square. So this works out to be 164.87 and this is less than 189.33. Hence design is safe. So this concludes the design problem. Thank you.